All right, morning everyone. Welcome to the next installment of the JKMRC Friday Morning Seminar series that take place here, typically at the Indoor-Pili Lecture Theater and online. My name is Katerina Savinova, and myself and Karina Barbosa will be taking turns introducing the speakers this year. On behalf of the University of Queensland and Sustainable Minerals Institute, we'd like to respectfully acknowledge the traditional owners, the Yagara and the Turrbal tribes, and their custodianship of the lands on which we meet today. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country. We recognize their valuable contributions to Australian and global society. So today we hope our audience is safe and dry. It's not a very big audience here at the Lecture Theatre, but we do have a healthy contingency online. Our speaker today is Dr. Artem Golev from the Center of Mine Land Rehabilitation here at SMI, where he currently works as part of the Development Minerals Group. He has 20 years of work experience in the minerals industry and academia, and he has been the principal investigator for SMI's collaborative research projects focusing on sustainability and resilience in metal supply chains since 2013. He has a multidisciplinary background in economics, engineering, and environmental science, and his research interests include e-waste, critical metal supply chains, integration of mine waste, reuse and mineland rehabilitation, climate change and mining, and sustainable regional development. And we also have Professor Daniel Franks, who will introduce the topic that Artem will be talking. The title of the presentation is Introducing Ore Sand, a Potential Solution to Global Sustainability Crises of Sand and Mine Tailings. Over to you, Daniel. Thanks.
Thanks very much, and welcome everyone to this presentation today. It's a very disruptive period here in Brisbane, so it's great that we can use these online connections to have a really healthy audience to share the work that we've been doing with you today. I'm actually beaming in from Chelmer, where there's a lot of my neighbours are quite flooded. So in addition to the acknowledgements earlier, we should also acknowledge the situation that many people in Brisbane are going through at the moment. Of course, and recognise that there's a climate change component to all of that. So today we're going to have a really interesting presentation on ore sand. Ore sand is a new term, a new topic, and we'll talk about it more in a moment. But it is part of the Development Minerals program here at the Sustainable Minerals Institute at the University of Queensland. Development Minerals program, what we focus on are the local materials used in local development. So here we're talking about construction materials, we're talking about links to infrastructure, disaster reconstruction. There's also agricultural minerals. So really we're talking about the minerals and commodities that are used domestically. And so there's huge links to lots of aspects of sustainability that we've not been focusing on typically in the past when we just focused on the metal sector. So the work that Artem's going to be presenting today is a collaboration that we've been conducting with the University of Geneva for the past year or a little bit more. It's really inspired by two main motivations, and Artem will flesh these out for us as he gives his presentation. But essentially, we have a very large amount of waste material produced as part of metal mining, most problematically in the form of tailings. In 2021, we actually published the largest repository of tailings facilities ever assembled in a publication, one of the Nature journals, Scientific Reports. And the scale of tailings production per year is in the vicinity of 13 billion tonnes per year. So that's like nearly 1.8, or a bit more than 1.8 tonne per person on the planet, right? So a huge volume of waste, and that doesn't actually include waste rock. So that's on the one hand. Now, on the other hand, we have this massive demand as a global society for sand. And that sand is needed for the construction of almost everything that we have, whether it's the glass on our devices or the aggregate that makes up concrete. Sand is really intrinsic to global development, and demand for sand is in the 40 billion or aggregate is 40 billion, 50 billion tons a year. So you have these two sustainability challenges. That sand comes from rivers often, sometimes also from crushed rock and terrestrial deposits. You've got sand in demand, tailings being produced. Is there a synergy, is the question. And so we've been thinking about this problem. There are some companies that are innovators in the field. So Artem will share with you some of that innovation today. But the final point I wanted to share with you before Artem's presentation is that we need to no longer think of this as waste repurposing. If we're to make changes and strides in circular economy, we need to think about resources as purposefully designed. And so we've come up with this term ore sand to mean sand that's produced as a byproduct of metal and mineral processing. And it's not an end of pipe solution. It's not trying to take the residue from metal mining and do something with it. That approach has had limited success. It's about thinking about mineral processing and sand production in a way that is equivalent in our thoughts to the production of metal that we're thinking to take out of an ore body. So without taking any further time, I'll hand over to Artem to present our work on ore sand. Thanks, Artem.
Thank you for the introduction, Daniel, and good morning, everyone. Before I start with the topic of ore sand, I would like you to step back a little bit and think about global problems and sustainability challenges that we're facing on the planet and why the resources sector is crucially important directly and indirectly, both as a solution and as an industry that causes sometimes those problems. So the first figure that I would like to share with you, and there are three of those figures, is carbon dioxide emissions or greenhouse gas emissions in CO2 equivalents, around 50 billion tons. We know that this causes overheating of the planet, and we know this is about the maximum we allowed to emit before we destroy the planet and the ecosystem. And all the international efforts currently focused on a decrease of this figure. So we have to go down, not up from now on. Ideally, by 2050, we would like to see something close to zero for the whole planet. The carbon dioxide emissions, they are indirect impact. So they are killing indirectly the ecosystems and all living creatures on the planet. But there are also direct impact from the resources sector. What is this direct impact? How we can estimate and minimize it as well? That's important to understand. So the second figure here is mine waste generation. It allows you to see the scale of the issue. This is by far the largest waste stream on the planet. It's by an order of magnitude higher than all of our urban waste combined. All of our plastic, green waste, construction demolition waste, metals, all of it, it's by an order of magnitude higher. And yet we don't really have a good statistics. So this is just an estimate how much waste we generate. And it will cause in some cases long-term impacts for centuries, if not even for thousands of years, such as acid mine drainage, for example. There is a little bit of downturn trend. You may know that we are trying to switch from from fossil fuels to renewable energy. So it will give us a little bit decrease in terms of coal mining and the waste coming from coal mining. But at the same time, we will be mining more other metals. So at the moment, the only trend for this material and for this waste stream is to grow. And the third figure that I want to share with you is also around 50 billion tons. This is the most consumed solid material on the planet. They're called aggregates. This is sand, gravel, and crushed rock. We need this for our cities, for our roads, literally for everything. And this is also a significant impact that we are causing on the environment. And the only prediction we have is to grow for this number as well. The most problematic probably part of mine waste and aggregates is sand fraction. We know that tailings facilities can fail, killing a lot of people and causing a significant environmental damage. But it's exactly the same with sand and aggregates extraction. When we remove sand from rivers, from coastal areas, it causes, in some cases, even higher impact and long-term consequences exactly the same. So people can die, infrastructure can be ruined. So we have to think about sustainable aggregates extraction as well. And we think that there is a little bit of connection between these two, and they can help, especially when we see that they're about the same. How can we reuse mine waste? You know, mine waste essentially is a crushed rock, and aggregates are also crushed rock. So there must be some connections. So there have been a lot of international effort on both sides, on the mine waste side and more sustainable mining practices. So you can see some reports here on the screen. And there were some efforts, more recent efforts in sand and aggregates sustainability practices, but there were no direct connections. So in this project, what we are trying to do is just to find a connection between them, to bridge them. And this is our recent report published just last week, where we trying to do exactly that, trying to see whether it's possible to find a sustainable source of sand and at the same time decrease mine waste. So this is our team on both sides. We have the University of Queensland. We are experts in mining and sustainability practices in mining. And we have our colleagues from the University of Geneva who have been working on sand issues for the last almost 10 years. So we combine our efforts trying to address these two crises. So what is sand and what is ore sand? Probably this is what we have to start with. Not everyone knows and doesn't know at the same time what is sand. Normally we think about beach sand, you know, when we imagine sand. But sand is very important in all sorts of ecosystem and infrastructure activities. So in the ecosystem, we have marine sand, we have sand in the rivers, we have sand as a protection on the beach. We also have sand underground. You know, the only reason our aquifers underground are very pure water is because of sand. And if you remove this sand, essentially all this water may become contaminated again. In infrastructure, literally everything, as I mentioned, is built on sand. It's not just our roads and cities, but also some products directly made out of sand, and as well as energy, even renewable energy such as wind turbines, solar panels, they're also based on sand. You would be surprised, but for the solar panel, you need several layers of very pure glass, and glass is made out of sand. So if you don't have sand, you cannot really make even a solar panel. So when we combine, when we put these two figures next to each other, mine tailings generation and sand use, so they are on a similar scale worldwide. So the question is it possible to recover sand, or is it possible to produce sand by design, and then where we can substitute this sand? Can we use it for concreting, or can we use it as a fill material? Or can we use it for some industrial applications? In industrial applications, usually it's called silica sand, but it's not the only type of sand. So we decided to give it a name to distinguish it from waste. For a long time, there were efforts to reuse mine waste in different areas, but normally it's a direct reuse. It's not built on purpose product. So the ore sand, we're trying to distinguish and tell everyone that that's something that we process and recover as a product by design from mineral processing. So it may be a different color, it may have some different properties, but it's exactly the same with natural sands. We have river sand, we have marine sand, we have manufactured sand, and in most places around the world, it's obviously subject to the existing rocks and mountains and rivers, so it may as well vary quite significantly. Early on, we also looked at different commodities that we have been already working with, such as iron ore, copper, tungsten. We, at the Center for Mineland Rehabilitation, we're also looking for benign materials production. This is important for land rehabilitation. If you make another step forward, essentially you can get to the construction aggregates type material and quality. So it can be coming from copper or tungsten mining. This is all based on silica content on this slide, but it can be also carbonate content, for example. And you know, they're all very small particles. So what does it make a good product? What does it make a good sand? This was one of the first things that we wanted to understand through the project and trying to kind of find a solution. Before I go first, one important note is on the market. we all know everything is driven by money. So how is significant the sand market is? We know a lot of efforts around critical minerals at the moment, such as lithium, rares, or cobalt. They are very, very small markets on the global scale, so you hardly can see them on this graph, but we know they are important. Then we have bigger markets such as nickel, copper, or iron ore. And iron ore here, not even as a metal, just as a concentrate, and yet it's still bigger than other markets. But sand and aggregates is so massive in terms of tonnage, but even being very cheap material, it's still bigger than all other markets. So this just gives you an idea that indeed, if we try to produce construction aggregates materials as part of conventional mining, we can find a market, not just in terms of tonnage, but also in terms of value. So Vale case, this is one of the first companies producing ore sand on a scale. So we try to understand how they do it and how good the product is and what are the challenges. We did an independent sampling of Vale sand in Brazil in July last year. So here you can see at the back the stockpile of white looking material. So essentially it's a stockpile of sand. So and then you can see also some train trucks filled with sand. So they produce it on scale and they ship it on scale mainly for roads and construction applications. So we went to the plant. We were able to see how it is recovered and produced. So it's not a waste material. It's really a byproduct. So it has to be filtered, it has to be dried before it can be stockpiled and then sent to the clients. So we took this material from the conveyor belt, you can see also this on the slides, and try to analyze and understand this material a bit further. So before we go into the results, this is a flow sheet. So it's important for us as a center, as an institute of mining, and as here as a center for mineral processing, to understand how do we recover sand. So in a very simplified way, iron ore processing, we have three major fractions to recover iron: a bit coarser, medium size, and very fine fractions. This is essentially what makes sand. So in sand as a product, you need to see the presence of all different size fractions. This makes it a very good product suitable in most applications. Then we can recover a bit of iron ore, then we can recover a bit of iron ore for the medium size fraction. And then we have our sand just as an additional step. Essentially, here you can see it's just extra 2 steps, and we recover it before it becomes waste, not after, but before. 2 important probably notes to make here. The sand that comes out, it's very fine, relatively fine. And the reason for that, it goes through several grinding and regrinding operations. So we believe there is an opportunity to improve this in the future, but at the moment, even as it is, it's a big step forward, and it's definitely not a waste material. So now the results from material characterizations. In construction, it's, you have to switch your mind a little bit when you characterize and try to understand what is good and how do you measure whether the material is good. It is often not just characterization in terms of chemistry and mineralogy, it's more about behavior of the material. So in construction, you have to know that physically the material will behave well, and many tests are designed well. But fundamentally, if you try to understand when and why the material going to behave well, it comes to 3 important aspects. The first one is particle size distribution, and you can see it on the first graph. The sand has to fill all the holes, and then if it's concrete, and then the cement will glue it together. But you need to see this representation of different particle sizes to make it very strong. Currently, Vale sand here, it's a very fine sand, so we cannot really compete with some other sands directly, but indirectly, in the form of blending, it's still a very good material. The second important part for properties is mineralogy. It may define both physical as well as chemical behavior of the material. So in our case, we have mainly quartz-based sand. So it's a typical, it even looks like river sand. So it's the same yellowish, whitish color. The only difference is that we have in the fines, which is kind of good and not so good. In the fines, it's mainly iron oxides. From health and safety perspective, it's actually very good. We were expecting to see a lot of fine silica, which is a health hazard, and everyone knows that. But there is hardly any silica in the fines. It's mainly iron oxides. And even if when you touch it with your hands, you can kind of visually prove it, it becomes black. So all fines particles are essentially iron oxides, hematite in this case. And the third important fundamental characteristics for sand is shape of the particle, shape and texture. It also, comes back to the strength of the material and how well it bonds together and stick together. So that's fundamentally important in construction applications. In our case, we mainly have a very angular, which is typical to manufactured sand. A little bit more details for material characterization. First of all, it's mainly silica. There's still residual iron oxides, and no surprise, it comes from iron ore operations and hardly anything else. So some minor other minerals. So that's a very good starting point for sand. We have very, very low trace elements. That's as well important for sand. In some cases, sand has to be used for water purification. So we have to know that there are no heavy metals. That's very important. And these trace elements levels here, most of them are even significantly lower than average soil characteristics. And the last point is, I would like to highlight here is leaching results. We also try to understand what if we're trying to leach the material the same as we would do for any waste material. So essentially nothing coming out, but that's no surprise. We don't have really any heavy elements present. Particle shape, another important parameter to understand. Think about it as building a sand castle. So we know that some sand is very good. You can make a very good sandcastle, and some doesn't really stick together very well. And that's very important characteristic in construction application. So where desert sand would be, probably on this graph, it's a two-dimensional characterization based on sphericity and roundness. Desert sand would be somewhere on the top right. So you can't really make a sandcastle out of this material. But then we have river sand, and then we have pit sand. So they are a little bit better, so they stick together better, especially when wet. And then we have manufactured sand produced on purpose from crushing rock. These ones stick very well together. So that's if you are about to make sandcastle, you better use manufactured sand. So the question is, where is our ore sand and where is Vale sand? So what type of processes do we use? Of course, we also use crushing, but in addition to crushing, we also use grinding. Most manufactured sand only use one stage, crushing, and that's it. There is no grinding involved, just to save on energy and to improve the properties of the material. So we believe it's somewhere here. We use data from the mineral liberation analysis, MLA. I'm proud to say this is a method developed at JKMRC. So in some sense, it's our in-house method. Apart from mineral characterization and liberation analysis, it also gives you information about the particle shape and size, of course. So based on this information, we were able to confirm that, yes, indeed, it's somewhere as we expected it should be. Geotechnical tests. This is how you can actually confirm that indeed materials stick together very well and will behave very well, not just in sandcastle making, but in all other construction applications. And the results are very promising. It's indeed sticks together very well. Just to tell you that without going further into details. Importance of particle size and particle shape. One more example, we recently had a conversation with a company called Kaya Sand, based in New Zealand, but also with an office in Australia, in Brisbane. So they produce manufactured sand. This is an equivalent probably of crushing ore in mining. And manufactured sand has significantly developed and evolved over the last 20 years. The volumes of production increased just because we want to substitute natural sand. They're trying to produce it again in a very simple way and very efficient way with minimum energy and to achieve the best possible results. And to do that, you're looking for particles more like cubical, not needles, not flakes. So there are specific technologies that you need to use to achieve just that. And then, of course, the particle size distribution, what they are looking for manufactured sand is to achieve the balance between different size fractions versus most natural sands. They're not very well balanced. You have to kind of blend a little bit. And versus some waste materials again. So that's something that we can keep in mind if we are thinking into the future. How would we change our crushing and grinding operations to achieve a better outcome? What if we start crushing our ore exactly the same way as manufactured sand? And then we can have perfect particle shape. We also can screen it on different sizes. And what would this mean for mineral processing, for flotation, or for density separation, or for magnetic separation? What are the consequences? But for purely from the sand perspective, this would be very beneficial. Apart from direct characterization, we also did some trials, magnetic separation and gravity-based separation. What we were trying to achieve is to see the potential of the material, whether we can improve the properties. In this case, mainly looking at silica content and the residual iron oxides. This opens other markets for sand. You know, when we go from left to the right on this graph, essentially we can increase the value of this material about 10 times. It really depends which market you are trying to target. So that's important to understand, not just construction applications, but also industrial applications and where else you can use your material. And on this graph, you can see mainly industrial applications, because in construction, you're looking for other properties, not just silica content. But for industrial application, this is usually the driving parameter. Construction application would be in the red sector over here, so that's they can accept other minerals, other elements, while in industrial applications you really have to look for silica content. And with our test work, we were able to see that we can indeed cover other markets and actually can satisfy the requirements, which opens opportunities for raw sands significantly. We also did some analysis of the emissions directly coming from ore sand recovery. At the moment, the preliminary results show that they're very low compared to other types of sand, but the sand usually is a very low impact anyway, so it's around 5 grams per kilogram or 5 kilograms per ton of CO2 equivalent emissions. But ore sand can provide significant benefit here. However, it's important to remember that this material can be transported over longer distances, and this is where the real emissions come into play. So, when you go beyond 100 kilometers transportation via truck, then essentially it's not that significant. Whatever your production emissions, they are less significant. But if you go via train or shipping over ocean, then again you can increase the distance of transportation by several hundred of kilometers. So can we scale up ore sands? So what is our potential globally for this material? And the first important slide that I want to share with you is, we have to think about sustainability. It's not just recovering byproduct and selling it. We have to see a broader implications from sand recovery. And the first point to make is to limitation of direct mine tailings reuse. In some cases, we know companies would tend to use it directly rather than reprocessing and claim it as a construction material, but there are significant limitations for direct reuse, and we have to be aware of those. Even if we recover ore sand by redesigning our processing operations, we still may face some limitations, such as presence of sulfide minerals or clay, or in some cases salts and coal, toxic elements, and in some cases even radioactive elements. So we have to look into those aspects as well. Then residual tailings management at the site. It's important as well to understand how do we manage landscape, how do we manage waste facilities at the site, and what is our plan for mine rehabilitation and returning this land back to nature after we finished with mining. So that's important to know how ore sand would fit in those areas as well. And of course, there are existing players on the market, and sand is mainly mined by artisanal and small scale miners, medium-sized operators. So we have to know how we can affect, because mining industry, if you scale up, it can overwhelm the market with volumes, especially locally. So we have to know how to balance social economic aspects of the regional development as well. But if we can overcome all of that, so what would be the potential globally? So we tried to understand, and we mapped the sand consumption first. In the blue color here, you can see areas where we consume a lot of sand. It directly linked to population, to gross domestic product, to infrastructure investment. So you can see a lot of blue in China and Southeast Asia, in India, but in some other places as well. In red color, we mapped the current tailings generation, again, globally. There are places where they are separate, and there are places where they very close to each other, and these are the places where you would see the major benefit from producing and recovering ore sand and substituting existing sand taken from natural ecosystems. So if you distance, again, back to the distance of transportation, it's important to know how far we are from the market. So our colleague, Martin Stringer, was able to map this on the graph. Roughly half of the global sand consumption is within 100 kilometers of a potential ore sand. So this is a very promising result. And if we start recovering on the scale, we indeed can find a market for this material. But ideally, this transportation distance would be more like 50 kilometers. This is where you would see the real benefits. So for the 50 kilometers range, we also were able to classify it on a country basis with absolute substitution potential as well as with relative potential. So for absolute substitution potential, China is obviously the leading country because they have a lot of infrastructural development. They need a lot of sand, and this is a logarithmic scale. So it's not even it's even more dramatic, overwhelmingly dramatic kind of picture. But other countries have also a quite significant potential for raw sand as well. India and Mexico and South Africa and Philippines. In terms of relative potential, there are some other countries that appear, countries where ore sand essentially can cover most of the market of sand. So such countries as Armenia, Fiji, or Jamaica, all of the potential ore sand sources are within essentially 50 kilometers transportation distance, so they can cover most of the sand demand in the country. And then, of course, we have Chile. Chile has a lot of mining activities, and most of the mines also relatively close to where sand is needed in the cities, and then followed by South Africa as well. And the last slide that I want to share on this analysis is how much, from a mining company point of view, how much sand you can sell, and how many mining sites would satisfy this criteria. And our analysis shows that around 30% of mine sites are within the transportation distance. So they can find a source, and it's a very positive number, 30% of mine sites. This is by number of sites. If you go on a tonnage basis, that would be significantly lower number because some big mines are far away from cities. But purely from the number of sites, it's very, very promising. And if we produce not just fine aggregates such as sand, but also coarser aggregate materials, then we will have even more mine sites with the possibility to sell aggregate materials such as crushed rock, simply, or benign rock. So we will be able to find the market for those materials. And some conclusions. So ore sand is a product by design. It's clearly not a repurposing of the waste. So we have to think about, and from pure marketing perspective, it's important to have a name, attractive name, so companies would be proud of it. So we're not selling waste, but we are selling a product, and it's the most benefit comes sometimes not just from tailings reduction, but also from substituting natural sand. So trying to avoid dredging of sand in the rivers or taking sand from the beaches. So it's an important side effect. So we have to kind of market exactly that. Then we still have limitations. Current limitations is mainly with grain size. So it's mainly fine sand. So we have to think about coarser materials. And we know that there are new technologies coming that will allow us to produce coarser materials. In terms of the market and as well as tailings risks, we know that major tailings risks are where these facilities are close to cities, but this is where the market for sand is. So those facilities probably have very good incentives, or should have very good incentives to produce sand and aggregates and essentially eliminate tailings storage facilities that are close to humans. We still have to remember about sustainable transitions. So we still have to address some technology issues and technical aspects. How do we recover sand and manage the contaminants and rehabilitation at the site? But the future markets are very promising. There are a lot of places all over the world where we can find the market. And I didn't mention when I was showing the slide, we actually can do the same analysis, not just on the country basis, regional basis, but we can also make it on the commodity basis, where the copper mines are, where the iron ore mines, and see which one of them would be more promising or closer to the market, as well as on the company basis. In some cases, limit to our database, but we can do the same analysis on the company basis and see which company is actually should go ahead first, because they have a lot of tailings very close to cities and very close to humans. And on this note, I would probably finish my presentation. And if you have more details, please, would like to know more details, please contact us and we will be happy to answer them.
Thank you. That was fantastic. Do we have any questions in the audience? And I think we have some questions online, but in the audience first. We do. It's great.
Okay, we have 3 questions, but we might check again online, but with the audience. But first question is: you may cover this, but I'll put in the Q&A to ensure. Did you review issues of potential metals leaching from the sands generated as waste from mining or other sources as well? I think you did mention that, but anyway.
Well, the short answer, yes, we did. We know about that and we recognize it. It comes back to mineral processing. We can achieve very high purity when we produce mineral concentrates. We know that many heavy metals are impurities. For example, for copper, we know we don't want to see arsenic in the copper concentrate, so we have technologies how to remove it. It's no different for sand. There are some elements that are not welcome, some elements that would limit your market application. It's, when you use it for road-based material, it's a bit different to when you use it actually, let's say for sand pit where children can play with this material, or for your home to build a house. So you have to address both. You know your market and what is the limit, and you have to know your mineral process and what you can possibly achieve and how you do it. Another important part, when you do leaching, it's not just the content. Many natural sands, they also have high heavy metals. They have presence of pyrite, for example, but that's a matter whether it will be leaching out or not. If it's inside the particles, if it's not exposed, in some cases it's still acceptable because it's not going to be affecting the environment. It has been weathered already. So it's exactly the same in mineral processing. You have to know not just the presence of it, but the behavior, which comes back to leaching behavior.
Okay, there's a few more online, and they're mounting up. So the next one is: are there tailings types that are just not suitable for ore sand generation, and the person's thinking of really high sulfur or sulfate outputs that would struggle? Or is there, I guess, a threshold somewhere where you said, let's not consider this deposit?
Yes, I believe there are limitations, and the first limitation is simply particle size distribution. If you grind your material too fine and you literally have, hardly any coarser particle left, that's, we cannot just glue them together. If they are all below 100 micron or below 75 micron, this is usually the limit. There are sand producers and sand markets, they want to see a very limited amount of minus 75 micron fraction. For manufactured sand in Australia, the limit is 20%. So if you go above 20%, so you're not satisfying the criteria, even if the material works, it would be hard, to claim that it's a good sand. So that's the first limitation. So you're out right away, unless you start changing the way you crush and grind the material. The second probably limitation is the mineralogy. If you don't have much quartz, much silica from the start, so that's essentially you don't have the minerals that's required in sand. That would be a limitation. If your tailings are mainly pyrite or other sulfides, then again it's no go right away. But in most cases you have both. It's a balance. So most cases still can find some opportunities.
Okay, we'll go on to the next one online, which was thank you for your insightful presentation. I would like to know if Vale and or other mining companies have tried to apply this concept to other mineral commodities. I know you touched on that a little bit, but I guess it's the range of mineral commodities that you know of that have had this sort of analysis applied to them.
We haven't heard on the commodity basis. In the Vale case, they have been trying for a long time to recover silica-rich materials just because they naturally have tailings enriched in quartz. So that they always knew that, and they always knew that there is some potential. And most recently, with the ban on upstream tailings dam facilities in Brazil, there was additional incentives from the government. If you're not allowed to generate such significant amount of tailings, so you have to find a solution. So they were driving as well by regulator and trying to scale up existing initiatives very quickly and find the market. There are examples, many companies try to produce it on a smaller scale. You probably can see it all over the world. The major difficulty to find those examples, it's in many cases, companies don't tell you that they're selling waste or sand from waste. They just would call it sand. And then you're not aware that it's actually coming from your mineral processing operations. One company here in Queensland is in northern Queensland is Mount Carbine. So they have a quarry and a tungsten mine on the same essentially site next to each other. So they can produce they are producing aggregates as well as a sand fraction from crushing waste rock, for example. So that's also an existing example, but that's a much smaller scale. So that's at the moment it's mainly company-driven initiatives. It's not a massive kind of initiative. This is what we are trying to achieve. Scale it up and bring it to an international at the international level.
Okay, there's still none in the room, so I'll go on to the next one. So this question says, I'm surprised what fraction of the tailings you analyzed or of the potential product you analyzed is within that usable reach of less than 50 kilometers. And this is far more promising than I thought, says the questioner. I also approve of the positive naming as a product, not as some sort of waste reuse, which has suppressed take-up previously. Are companies including a specific sand stream that may result in modifying the process route or adding a separation stage to produce a coarser or cleaner stream?
So I think there were several questions
in
this comment. Yes, we were also surprised to see so many companies to be close, but this is what the analysis shows. And just to kind of highlight again, this is on the number of mine sites, not on the tonnage basis. On the tonnage basis, there will be significantly less than that. But on a country basis, on the other hand, it doesn't depend on the mine sites. It just depends on the overall tonnage, and this is what we see as a promising outcome. So there are many countries where this would be clearly would be the case, and they may have a potential market for ore sand if it is recovered. So what was the second part of the question?
I've got to get back here. Something happened on my. Sorry. I've got to go to the answered questions. Where is it here? Yes. So the second part is: are there companies that are including a specific sand stream or modifying their processing to produce a higher value sand product?
Yes and no. And yes, because we know that the particle size distribution is important for companies generally, and how much you do of crushing and grinding. With lower grade materials, companies tend to fight against it with coarser processing. It's pre-sorting. It can be X-ray or optical sorting. So, and there are many companies who are introducing these technologies purely for the mineral processing to make it economic. But at the same time, when they give you the flow sheets, you can clearly see ore comes in, and then and then the first output coarse aggregates, and then the second output sand. They even call it sand because it's on the sand fraction. And then the third, fine sand, and then ultimately they have tailings, and the tailings go to the tailings dam because they're very fine. But there are several coarser materials that coming out simply because of pre-sorting and coarser processing technologies. So this is very promising for raw sands in general. Some companies are interested; they do look into that. So we do hear these stories, but not yet on nothing yet, on the market. So we want to see this not just initiatives and trials, but to be actual product on the market, not yet.
Okay, we're going to the next one. I'm thinking I know the answer to this already, but so it's what's the approximate cost of modifying or building infrastructure or technology to allow for mines to be able to process what otherwise would be waste into ore sand? So new technologies or different infrastructure to do that.
Really depends on the case-by-case basis. There is probably a limitation because sand is a very low value product, or relatively low value, depends on what type of sand you produce. We see it as a low to medium capital cost for that material, because that's just the nature of the material, how you recover and produce it. You can use gravity-based separation. So this is what we were trying to see. You can use flotation. It's also relatively low cost. They're probably the bottom value for sand worldwide is about $10 per ton. So whatever processing you use, if you can maintain your cost significantly lower than that, then you can justify it. Not to mention that your cost for having tailings and managing the tailings dam, you can also save over there. That can be very significant savings as well. And the cost to build another tailings dam and maintain it are very, very significant. And I'm sure when you compare them, the cost of recovering sand, the capital cost and operational cost will be significantly lower than in many cases management of tailings.
So Artem, it's a bit of a question and a comment. So the question is really around when you've looked at the volume of tailings material in your analysis, you've just considered the total volume, not the volume that is in the right size fraction.
That's correct. That's correct. There is not much information even on the total tonnage of tailings. No one knows. Daniel mentioned that they did publish last year, or 2 years ago almost already, the paper on the tailings dams review, but that's just total tonnage. No one, and it's still only, a third of all tailings dams in the world. And no one knows the exact characteristics. Some companies don't even look into those characteristics. Even if they do, they don't report this information. And even if they report, over time, the weathering changes the nature of tailings. So it will be a different material when you start thinking about reprocessing. But in our case, we are trying to articulate that it's not about all the tailings. It's more about new tailings produced. So you have to avoid new tailings generation. This is where you can do it more economically and feasibly. Yes, there is a potential for all the tailings as well, but it's at the moment is not our major focus. The major focus is current and future tailings.
So that sort of leads to the comment where I think from those previous questions and what you're saying, the opportunity is actually how do you get that coarse barren fraction out as early as possible to lead into this product? And there's probably, you could probably justify a capital cost to be able to do that as long as you don't lose the metal recovery in doing that. And it would be interesting now to go back and have a look at the total tailings with a view of what fraction in the current processes would you be able to pull out. And in a number of those cases, I think it's probably quite small unless you put a different process step in place. So that's the big opportunity. I mean, I think it's huge where you could probably get quite a good matching of what is needed in the region with what you could get out of existing processes if you change the front end slightly. So yeah, very, very exciting and interesting. Interesting to do a bit of a mass balance around those circuits. And I think that data is available. It's just knowing where to go and find it.
Yeah, just maybe to add to that, we did consider, the potential, what would interest companies. So our threshold was 10%. If you can recover 10% of your tailings as sand, then this should justify the case. And this is what we used as a threshold. And in the Vale case, that's also comparable. They're looking at a bit more than that at the moment, but that's the lower range. You don't need to recover 100%. We're not saying that. Even 10% is a good enough number.
So a very simple question, but I'm not sure if the answer is simple. What is the value of sand in US dollars per ton?
The value of sand for construction sand, you can average as $10 US per ton, but it really depends on the market and what type of sand. The cheapest sand probably is from marine region, where you have big ships near the coast. Obviously, you better be near the coast, so you don't ship it far away. It can be as low as $3, let's say, or $4 per ton. River sand usually more expensive, but better quality. Doesn't have salts. In the marine sand case, you either limit your areas of application, or you have to wash it. And when you start washing it, you add extra cost. It's cheap to dredge, but then you have to wash. Pit sand probably similar to river sand. Again, it also depends where you are in terms of a marketplace. In the city, the sand price can be, let's say, 5 times higher, because this is where you need sand, and this is where and the sand is usually a very small fraction of the total costs. So companies don't mind to pay extra because it's kind of very low share of their costs anyway, as long as it's the right sand and it's in the right place. So it also kind of makes it difficult to estimate the market. So what is the market? Do you measure it as a sand price in the city or as a sand price at the quarry basis? Because the transportation in many cases is their major cost, not the sand itself, but how you're transporting it from one place to another. It can double or triple your costs and the value of sand.
Great. We still have 4 questions left, and we've got 7 minutes. So as long as you don't mind, we'll keep going. So here's another one. Thanks, Artem. Very good presentation. Have you thought about doing a life cycle assessment of ore sand versus conventional sand? If so, which country or region would you choose? For instance, Brazil, given your project was with Vale?
We did life cycle analysis. So this is in our report, life cycle analysis for Vale sand, and comparing it with existing data in the literature and in databases for life cycle analysis, such as EcoInvent. But in life cycle analysis, it all depends how much data you have and how detailed you want to go. So we didn't go into very detailed analysis, just a more high-level analysis, and it does show clear benefits. Brazil is as good as any other country, so I don't see why not to use other country. But at the moment, the only mass-scale production of sand is in Brazil, and it's Vale. So that's why we were looking at Vale, but we are happy to look at other countries as well.
Mm-hmm. I think you've answered this one already a little bit, but the next one is, have you explored other uses of sand from tailings besides aggregates, perhaps new value-added products, ? The high proportion of fine particle sizes in tailings is indeed a disadvantage for the aggregate industry.
Yes, in fact, most of my career was about looking into different byproducts, and then recovery and from waste or eliminating waste. So this is what I have been doing for more than probably 20 years. And there are opportunities. It's not just aggregates. In fact, I didn't mention during my presentation, but I did mention it before for other seminars. In some cases, especially when we're looking for abandoned mines and when we're looking for critical minerals, the value of critical minerals is so low that it's almost impossible to justify reprocessing this material from a pure economic point of view. You just cannot, that's massive amount and very low ppm level, metals in there. But if you add ore sand or aggregates as an extra part, as an enabler, which would cover the basic processing, because $10 per ton can cover your gravity separation, flotation stages where you would recover concentrate, and it can pay purely on the value of aggregate, and then it allows you to recover something else as a byproduct. Then your critical metals would be a byproduct, while your major product by volume and by value is actually aggregate material. So that's an important enabler in some cases for future mining.
Great. We're on the home stretch now. Thanks for the presentation. I would like to know if you can explain about the process of magnetic separation Vale is using. Do you know if it's dry or wet?
It's a good question. I cannot really answer. I believe it is, in this particular mine, it is wet. I might be wrong. But what I do know that Vale has some mines that are completely using dry processing. In the northern region, everything is dry. There is no water involved. And what Vale wants to do is to make all their mines in the future dry. And they are kind of looking into different magnetic separation methods to completely switch to dry processes, no water, no tailings dams, no dewatering needed. But this is the future for Vale, at least, and maybe the future for other companies.
Any?
Oh. Just excuse me, just a quick one. I liked your presentation because you covered a lot of bases, which is fantastic. One thing I feel is worthwhile a little bit of attention is ultimately you've got tailings still, and they're ultrafine tailings. What about stability of tailings dams with this new type of tailings? I mean, the mining industry goes to a lot of trouble to make sure that their tailing dams are nice and stable by adding coarser material to it, for example. That's one of many things they do. Have you given any thought to this issue?
Yes and no. For this project, no, we didn't look into that, but I did look into that in some other projects. Some companies have fine material only. There is nothing coarse. And there were many examples where, the only way to find a useful use for those materials is to aggregate them back. Even in the case of iron ore itself, they recover very, very fine iron ore, but you cannot sell it because steel companies cannot really use, they have to make pellets. So it's an aggregation process. In some cases, you may need to look into exactly the same method. You have to aggregate the materials, and then you may find either a better storage solution or a beneficial reuse. There is still value in the fines, depends what minerals in the fines. But what we're trying to do first is to minimize the volume of the material to manage. If it's a very low volume, then it's much easier to find products or potential products to make out of this material.
Okay, final one, I think, is hopefully pretty easy. Is there any relation between the bulk density of the sand and the end use of the sand?
The bulk density, yes, there is a direct link. The simple reason for that is, the material has to be structurally sound. Ideally, you would have something very strong and very light. We know some critical metals, that's exactly why they're important, or I don't know, scandium aluminum alloys or titanium alloys, they're much lighter and much stronger. So the same with construction aggregates. Ideally, you want to see something light, like quartz is relatively light and strong, while magnetite, 2 times heavier mineral and not as strong as quartz. So you don't want to see that. And what it means, you may limit applications. So the sand simply cannot support the same structure, the same weight. So you would need to use it in a different application. So that this is something that's important to kind of remember and note. But on the other side, there are cases the other way around where you're actually looking for heavy material because you really want in the same space to fit something that is very heavy. And then it's just a different area of application.
Thanks everyone for a very good discussion. Let's thank Artem one more time. Thank you, we're right on time. And next week we have Professor Andrei Van Ask from the Bryan Research Center here at SMI as well, with a presentation on the state of deep mining geoscience. We will see everyone then. Thank you.
Thank you, my pleasure.